We looked at derivatives of y equals e to the x and y equals natural log of x, in the last video, but these are just kind of special cases of exponential and logarithmic equations. There's really infinitely many exponential and logarithmic equations depending on what your base is. So for exponentials, I could have, say, y equals 2 raised to the x power, or 3 raised to the x power, or 10 raised to the x power. How would I take the derivative of that? How does that look similar or different than y equals e to the x? Or even natural log of x. It looks a little bit funny because we use a different notation, but that really says log base e of x. So if I had, say, log base 4 of x, how would I take the derivative of that? And that's what we're going to try and talk about here in this section. So let's erase these because I actually want to come back and talk about our special cases. Let's start with exponentials. It says the derivative of f of x equals b to the x is f prime of x. And before I give away the answer, I want to think about, well, how did I take the derivative of e to the x? We said the derivative of e to the x is just e to the x. It is its own derivative. It does not change. So b to the x is going to act really, really similar in that it starts off almost exactly the same. Well, if that didn't change, then this part I would expect probably should show up in my derivative as well, and that is the case. F prime of x is b to the x. But I can't just leave it as b to the x. We do have a little extra something right here, and that little extra something is times natural log of my base b here. And that is my derivative. So it acts in a way that's very similar over here to e to the x. We just have this extra factor of natural log of b that we need to multiply that by. Oops. The b to the x, hopefully you'll see that pop up again, and so it sort of behaves similarly, not exactly, but similarly to e to the x. Next, let's look at logarithms. So here I have g of x equals log base b of x. So if I want to take the derivative of that, think about how did we take the derivative of natural log of x? Well, we said the derivative of natural log of x was 1 over x. So the derivative of log base b of x, this is going to behave really similarly. It's going to start off as 1 over x. So already this looks exactly like that, but it is going to behave just a little bit differently. In this case, rather than multiplying by natural log of b, we're going to divide by that natural log of b. So that appears in our denominator. So times natural log of b. So hopefully we see that 1 over x is appearing once again. It is acting in a way that's very similar to the derivative of natural log of x. We just have to remember to account for this extra factor of natural log of b in our denominator. And here we just need to account for our factor of natural log of b. So that's really the only major difference between these. We just have this extra thing that we need to multiply by once we kind of repeat that same process or use that similar process of e to the x and natural log of x for our derivatives. So let's practice looking at a few derivatives. So here f prime of x, I have f of x equals 2 to the x minus 3 to the x. So when I go to take the derivative, f prime of x, and actually let me scroll up here so I can look at my formula. So okay, if I have 2 to the x, then the derivative should look like 2 to the x. So 2 to the x, that part stays exactly the same. I just have this extra factor of natural log of whatever my base is. Well, in this case, my base is 2, so times natural log of 2. And that's it. There's the derivative of that first term. So I can continue on then, and I can say, okay, well, minus the derivative of 3 to the x. So this time I've got 3 to the x. So the derivative of that will be 3 to the x, times natural log of my base, well, times natural log of 3. And there we go, there's our derivative. It's going to be 2 to the x natural log 2 minus 3 to the x natural log 3. In part B, let's see, I want the derivative of log base 4 of x minus natural log of x. So f prime of x here. So log base 4 of x. This looks an awful lot. Let me erase these. this looks an awful lot like log base b right here. So it's going to start off the same. It's going to start off as 1 over x. So 1 over x, 1 over x. In my denominator, though, I just have this natural log of b, where b is my base. In this case, b is 4. So in my denominator should also have a factor of natural log of 4. So 1 over x times natural log of 4 minus derivative of natural log of x. We know that is just 1 over x. There we go. There's our derivative. We don't need to do anything else. So again, hopefully we're seeing that it behaves in a very similar way. Next up, I have g of x. I've got log base 8 of x minus log base 5 of x to the 6th. Here, hopefully you look at that and have an eyebrow raised and say, well, when we had x raised to some power before, that was an awfully big problem. And those log properties that we talked about for natural logarithm, it turns out to be the case that those are true for any logarithm. So I can actually apply those same rules in this example right here, even though we don't have a natural logarithm. So before I even take the derivative, before I find g prime, I'm just going to rewrite this expression. I'm going to rewrite it as log base 8 of x minus 6 times log base 5 of x. And now I'm just going to take the derivative of each term separately. So g prime of x, derivative of a logarithm, it's going to start off as 1 over x. I just have to multiply by natural log of my base, which in this case is 8. So times natural log of 8 in my denominator. Minus 6. Here 6 is a constant multiple again, so 6 times derivative of log base 5 of x, derivative of a logarithm, that's going to be 1 over x, times natural log of my base in my denominator. My base is 5, so times natural log of 5. So really I've got 1 over x natural log 8 minus 6 over x natural log 5. There is my derivative. Lastly, part D, derivative of x to the 10th plus 10 to the x minus 10e to the x. Here f prime of x, x to the 10th. That's a power rule. So okay, I'll multiply by my power, subtract 1 from my power, 10x to the 9th. Plus here I have an exponential, so it's going to start off as 10 to the x is going to be exactly the same. I just need to multiply that by natural log of whatever my base is. In this case, my base is 10. So times natural log of 10. Minus here, be careful with this 10. Remember that that is a constant multiple, so that doesn't go away. I just multiply that 10 by the derivative of e to the x. Well, we said the derivative of e to the x is just e to the x, and there is our derivative. So just be careful with these. We won't see them as often as, say, y equals e to the x and y equals natural log of x. The vast majority of the time, these are the two that we're going to be using. But every now and then, we may see some of these pop up, especially in applications problems. So if I wanted to look at an example where I might want to use this, I have an investment of $25,000 earns interest at an annual rate of 8.4% compounded continuously. Boy, this sounds an awful lot like the types of problems we were looking at in 3.1 in the last section. Well, it's because it's the exact same type of problem. It says, find the instantaneous rate of change of the amount in the account after 2 years. So here, I've got A equals P times E raised to the RT power. This one's a little bit tricky, but we can start by plugging in what we know. An investment of $25,000. That's my starting amount. So $25,000. E, we know that's a number. Earns an annual interest rate of 8.4%. So 0.084. Now, what am I trying to do here? I want to find the instantaneous rate of change of the amounts in the account after 2 years. So if I were to just plug in, if I were to just plug in 2 right now, And that would tell me exactly how much is in the account right now. That would tell me the current amount in the account. But I don't want that. I want the instantaneous rate of change. I want these words right here, instantaneous rate of change. That should be like an alarm that goes off in your head. Instantaneous rate of change, that's code word for derivative. So I can't plug 2 in right now because then I would get a constant, and I know that the derivative of a constant is 0. So what I actually want to do is I want to think about kind of what's changing here. 25,000, that's my initial investment. The amount in the account is changing, but the initial amount that I start with, that's not changing. The annual interest rate is not changing. It's always going to be 8.4%. The only thing that can change here is t. How long do I leave the amount in the account for? So I'm going to leave this as t. And then here I'll have, we'll just leave this as a for right now. So I still need to take the derivative. But if I go to take the derivative right now, the derivative, this isn't quite e to the t. If it was the derivative of e to the t, I could deal with it. This is e to the 0.084 times t power. It's this 0.084, this guy right here, that's causing problems for me. So I need to kind of come up with a really clever way to rewrite this expression. And the way I'm going to do that is I'm going to say that this is 25,000 times e to the 0.084. Most of this all looks the same. All of this raised to the t power. So hold on a second. Am I allowed to do this? Most of the time we won't go in this direction. Most of the time we start here, we work our way backwards. We say, okay, if we have a power raised to a power, what do we do with those two things? Well, we multiply them together. So it's legal. I can do this. I am allowed to kind of make this transition, but why would I want to do that? Because now I can think about this as 25,000 e to the 0.084. That's not quite e, but it is a constant. So something like 25,000 times b to the t, where b just happens to be an exponential. It happens to be e to the 0.084. And I know how to take the derivative of this. We just said the derivative of that guy, we just said earlier, that's going to be b to the x times natural log of b. So I can take the derivative of this. If you need to, make a quick substitution. Look at this guy right here. Use that and kind of make a mental note in your head that b is equal to 0.084. Oops, not 0.084. It's e to the 0.084 power. That's our constant. That's our b. So when I go to take the derivative, a equals, so 25,000, this is a constant multiple. It's not going anywhere. 25,000. Derivative of b to the t, well, the derivative of b to the t is just b to the t times natural log of whatever my base is. My base is b here. But this isn't super helpful because I don't want this in terms of b, so I'm going to take this e to the 0.084 and plug that back in. Oops. So this is an a, I'm sorry, this is a prime, excuse me. A prime is equal to 25,000 times b, that's e to the 0.084 to the t power times natural log of e to the 0.084. So a few things I can do here just to clean this up. I'm going to take 25,000, actually, before I do that, natural log of e to the 0.084, that's just going to be 0.084. This part right here, 25,000 times e, I'm going to kind of rewrite this as e to the 0.084 t power times 0.084, and then I can multiply these together just to kind of clean it up, make it look a little bit nicer. So let me see what I get there. 25,000 times 0.084. I end up with 2,100. So 2,100 e to the 0.084t. This is my derivative a prime. Whew. Boy, I sure am glad we're done with that problem. Is what I'd say if we were done with the problem, but we're not. Because remember what we were trying to find. We wanted to find the amount in the account. And let's erase this so that we can kind of read it a little bit clearer. We want to know the instantaneous rate of change of the amount in the account after 2 years. So I have one last step I need to do here. I need to go to my derivative and plug 2 in for t. So a prime, I'm going to plug in 2. It's 2100 e to the 0.084 times 2 power. So 2100 times e to the 0.084 times 2 power. Let's see, I end up with 2,484.17. So that is my instantaneous rate of change, but I'd also like to be able to kind of talk about what this means. Well, what does this number represent? So remember that this is the derivative. This is the instantaneous rate of change. So this means the account value, or the amount in the account, we'll say the amount in the account is either increasing or decreasing. Well, we can tell again because this is a positive 2,484. So it's increasing by $2,484.17. And how often is it increasing by that amount? It's increasing by that amount per my unit of time. What was my unit of time? It was years. Per year. And then when is it occurring by or increasing by this amount? It's increasing by this amount after 2 years. After 2 years. And you can put that after 2 years here. I actually kind of forgot. I like to put that in the front, so I actually kind of like to say after 2 years, then the amount in the account is increasing by $2,484.17 per year. I think it helps to give some separation between this 2 years and this per year because it's really easy to mix those two things up. So here is what this number means practically. So this was a really difficult problem. This was, I will admit that this is a hard problem. I think making the substitution of e to the 0.084 as b, this is a hard problem. But this is an example where we have to be able to take the derivative of something that looks like this. If we can't, we cannot do this problem currently. So take a look at a couple of these. Again, we won't see these as often. I would really rather you focus your studying on the derivatives of y equals e to the x and y equals natural log of x, because those are going to be the most common examples of logarithm and exponential functions that we see in this class.